So here's an example of a chi-square test for homogeneity for you, EFOT. And this is actually one of the free response questions from the 2016 or one of the 2016 AP Statistics exams. Basically, they took a sample, or they took a group of 75 children, but those children were randomly assigned to one of three treatment groups, A, B, or C, described in this table. And so we wanted to see in A if the data provide convincing statistical evidence that there is an association between type of ad and children's choice of snack among all children, similar to those who participated in the experiment. So to address this issue, first we have to recognize that it is a chi-square test for homogeneity because these children have been randomly assigned to one of three independent groups. So we said one major difference between independence and homogeneity is that it's one sample with homogeneity, and then you just break them out within that sample by the categories, whereas I meant to say independence if I said homogeneity, whereas in a test for homogeneity, you have independent groups, and that's what we have in this case. So it would be a chi-square test for homogeneity. So with regards to our null hypothesis, just like in a chi-square test for independence where we say there's no association or that they are independent in the null, we're going to do the same thing here. We're going to say that there is no association between type of ad and the children's choice of snack. And in the alternative, of course, we're going to say that there is an association between those two things. So that completes our state. Now our plan is the same as our plan was for the chi-square goodness of fit test as well as the chi-square test for independence. We of course need to have randomization, and then we need our expected counts to be at least 5. So we're going to calculate those expected counts in the same way that we did for our chi-square test for independence. So a reminder with regards to how we go about obtaining those expected counts, we do the following. We go to our matrix menu, which is a second function key under x to the negative 1. And so we go second, x to the negative 1, edit, and then edit matrix A, which is number 1, and we enter our observed counts. Then we need to go ahead and run the test, so sort of do the do, so that by running the test, our calculator will store the expected counts in matrix B. And to do that, we go to our test menu, which can be found under Stat, Tests, chi-square test, which is option C. And here we don't need to change anything. We leave our observed matrix A, our expected matrix B, and we go on down to calculate and hit enter. And we can see our test results, which we will examine more closely when we get to the do. But what we're really interested in here are our expected counts. So to view those, we have to go back to our matrix menu again, which is second, x to the negative 1, edit, but this time go down to matrix B, which is number 2, and hit enter. And here are all of our expected counts. We can see they're either 18.6 repeating or 6.3 repeating in this case. So that completes our plan. We have checked for the expected counts to see that they are all at least 5, and we listed them. And then we also checked for randomization, and the children were randomly assigned to one of the 3 treatment groups. So we're ready to move on to the do. And in our do, it's important that we either identify the test by name or by formula. You can also do both, but if you're uncertain as to which type of chi-square test it is, then I would encourage you not to name it and just show the formula. Not a very good copy of that formula, but we'll use it here. So chi-square is found by, of course, taking every observed one at a time. So I'll start with the first observed, group A that chose Choco-Zooties, 21, minus its expected, which I see in the top left-hand corner of my expected matrix, about 18.67. Square that difference and divide by that expected value. And we need to continue to do that for the other observed and expected. So if I go across the row, top row, for the apple zooties, I observed 4. I expected 6.33. I have to square that quantity and then divide by 6.33. Oops. And then I can just show and so on for all other remaining cells. We know then that that comes out to a value, according to our calculator, of 10.29. Our degrees of freedom, remember, is the number of rows minus 1 times the number of columns minus 1. So in our case, that would be 3 minus 1 times 2 minus 1, which is 2 times 1, or 2. And then, of course, our p-value is crucial. Our p-value in this case is about 0.006. So that completes our do. So when p is low, we reject the ho and have significant evidence that the ha is true. So we're going to say that in conclusion. So because the p-value is very low, or you could say because it's below a reasonable level of significance such as 0.05, we reject the null hypothesis, which means there is convincing evidence to say that there is an association between the type of ad and the children's choice of snack among all children similar to those in this experiment.